Alright, silly people, here's the situation. We're in the infinite square well, and Griffiths says that there is an amount of time that you can allow to elapse from an initial time, t or 0, where the uh, initial particle state will bounce back to whatever initial state it was in some magical quantum revival time, capital T. Um, and he has a value for it that we're going to prove. And we're going to do that by having this as the most generic time independent initial state for any particle in the infinite square well. It's just a sum of all of the eigenstates multiplied by whatever constants they need to have, um, and then equate it to the most general time dependent wave function for particles in the infinite square well uh, at time capital T. So what I'm saying is we're going to say this is equal to x of t. Yeah. So, I mean, just equating the two equations, we've got sine n pi x over a here equals sum over n cn sine n pi x over a, and then the exponent term minus I n squared pi squared h bar capital T over 2ma squared, and we just have to solve for capital T. Um, so already we can cancel a lot of stuff out. The cn goes away and the sine function goes away. And we just have 1 equals to the sum of all exponents, exp minus I n squared pi squared h bar t over 2ma squared. And what I'm going to do next may freak you out, but I'll say right now the factor of n doesn't actually matter because it is just an integer, um, especially since it's n squared. Uh, we can kind of get the same revival time by setting n to any number. It'll be the same. So I'm going to set n to 1, and so we really just have the equation 1 equals exp minus I pi squared h bar t over 2ma squared, right? If you picked any other n, the oscillation of the particle would be faster and faster, um, depending on how high of an n you go. But after time capital T in this equation, it will always eventually end up in its initial uh, state. It just might end up being there earlier, depending on what n you choose. Um, so we can solve this not by taking the natural log of both sides, but by recognizing that if you uh, have the argument of the exponent equal to 2 pi instead of 0, you're going to end up again with the same initial state because 2 pi represents a full rotation. Um, so we'll have 2 pi be equal to pi squared h capital T over 2ma squared. Okay, now we can actually solve for t. And so this is going to be t equals 4ma squared. One of the pi's gets canceled out, so it's just pi h bar on the bottom. And I think even Griffiths got that, so we're good there. The next thing that Griffiths asks is what is the revival time if you happen to be in classical physics, not really in quantum physics. So the classical revival time uh, will just be the time it takes for the particle to get from one side of the infinite square well uh, to the other side and then back uh, to where it started. So The infinite square well has a width of a, so it has to travel a distance of 2a to get out and back again. And then that's divided by whatever velocity it has. That's going to give you your revival time. Um, you can find the velocity by treating the energy of the particle E as entirely kinetic energy, so mv squared over 2. This is the sort of thing you do in semi-classical arguments. And so we just solve for v here. We got 2e over m. And then we can plug that into this equation. So the revival time will be 2a over root 2e over m. And you can do a step of algebra, and you'll see that the revival time is a times 2m over e. All right. Last thing that Griffiths asks is, what energy value for E do I need to have for the two quantum revival times to be equal to each other? And so we just set the revival times equal to each other. So we have 4ma squared over pi h bar equals a square root 2m over e. Let's square both sides and take the inverse of both sides, canceling out a factor of a first. So we got pi squared h bar squared, or 16 m squared a squared equals e over 2m, and so cancel out a factor of m on the bottom and a factor of 2 on the bottom. We got e equals pi squared h bar squared over 8ma squared. And since we happen to know that the energy eigenstates for the infinite square well kind of look exactly like that, it's all the same factors, we can say that this is equivalent to E1 over 4. And that's interesting because we find that for the revival times to be the same in classical mechanics as well as quantum mechanics, the energy of the particle has to be smaller than E1, which is the smallest value of energy possible for a particle in the infinite square well. So it kind of just doesn't make sense in either quantum mechanics or classical mechanics now. The energy value is so small. And I feel like we do this a lot on this channel, but turns out whenever you treat a quantum mechanical problem as a classical mechanics problem or vice versa, you're kind of going to get an answer that doesn't make sense in either. So, funky.